Hi everyone. In this video, we will be looking at section 12.3. In class, we considered this example. Remember, if you have a population and you take samples from it, you can get different observations in your sample. So ultimately, if you estimate values from that sample, you can expect to get different estimates. So in this case, you'd expect a different slope parameter and a different intercept parameter. So the result will be different possibilities for your regression line. Ultimately, what this means is that beta hat 0 and beta hat 1 are random variables and hence will have sampling distributions. We focus more on beta hat 1 because it gives us a lot more information than beta hat 0. If you look at the way the line is formed, only beta hat 1 defines the relationship between y and x. The moment beta hat 1 is equal to 0, you just get a horizontal line. And your line becomes y hat equal to y bar. So what that means is like if I give you any information about x, you will not be able to tell me anything about y if you have no slope parameter. That's your beta hat 1. So in these two cases, beta hat 1 is not equal to 0, so there's clearly a slope, and it's clear the relationship between y and x. Now, what's the distribution of beta hat 1? Beta hat 1 follows a normal distribution with these parameters. You can immediately see that beta hat 1 has expected value of beta 1. So that means it is an unbiased estimator of beta 1. Now, if we have this information, we can now derive a confidence interval as well as a hypothesis test to test for different possible values of beta hat 1. So let's start off with this theorem before we look at the confidence interval. In this theorem, it is just telling you that if you have t that looks like this, then this follows a t distribution with n minus 2 degrees of freedom. So let's just see how they get this so you can see where it comes from. So remember in our previous slide, we said that beta hat 1 follows a normal distribution with these parameters. So let's just do a quick recap. Page 320, remember the definition of a t distribution. So this is how you form a t-distributed random variable. If z is a standard normal random variable, and you divide it by the square root of x over v, where x follows a chi-square distribution with v degrees of freedom, then this random variable has a t-distribution with v degrees of freedom. So you can rewrite this t like this. So this is where it's coming from, but it's simplified to look like this thing here. So remember, the numerator has to be a normal 0, 1. So this follows from this result. If you take beta hat 1 and you standardize it, you'll get a normal 0, 1. And then in the denominator, we know that this thing, just on that part here, has a chi-squared n minus 2 degrees of freedom. This is from chapter 6, so you can recap on that. And if you divide by its degrees of freedom, which is n minus 2, then this whole thing will have a t-distribution with n minus 2 degrees of freedom. So you can go and verify yourself that if you cancel the n minus 2's and the sigmas also cancel, so you end up with this result. Okay, so just note here, in order to simplify the notation, this S beta hat 1 that they have is just equal to this thing here. So this is just the sample standard deviation of beta hat 1. Now we can look at the confidence interval. So you could be asked to derive 100, 1 minus alpha % confidence interval for beta 1. So from our previous theorem, we know that this has a t distribution with n minus 2 degrees of freedom. So this is going to be your starting point in the derivation. So as you always start, this is the idea. So you want to find something that you can put as a lower bound and something as an upper bound, such that the probability that beta 1 is in between those values is 1 minus alpha. So you will start from this. So your pivotal quantity is this thing, which you know has a t distribution. So you can start off here and then replace this t with that value. Then all you have to do is manipulate this inequality so that you end up with beta 1 in the middle on its own. So you can do that. It's exactly the same as other proofs that we have done before, and you should make sure that you get this result given on page 644. So now if we have a look at this confidence interval, like why is it so relevant? Well, for starters, remember earlier when you would use your calculator and you would find an estimate for beta hat 1, or you'd use a computational formula, you'd get a point estimate. Now remember, a point estimate doesn't give you any idea about reliability and precision, but a confidence interval does. So that's one reason you definitely would want to opt for a confidence interval rather than a point estimate. Now, if we have a look here, I've got different graphs. You can obviously see that in this graph, the spread around the line, it's a lot less than in this case. Now, the fact that this data is spread out a lot less means this S is going to be smaller in this case than it is going to be here. And if you now compute a regression line, using this information here, you find that because your data is less spaced out from the line, the slopes can vary a lot less. So in other words, your confidence interval is going to be narrower when you have less spread around the line. So these are some possibilities of lines that you could get from that data. If you look at this example, now the spread is so much bigger, and if you try to draw a line, you could get a line like this, you could get a line like this. The slope can vary so much. So these are 3 examples of different possibilities. So this is just a graphical way of just seeing the influence of the spread of your data about the regression line on your beta hat 1 confidence interval. Now, let's have a look at example 12.2. In this example, the question we're trying to answer is it possible to predict graduation rates from freshman test scores? And I put in here matric because you can think of these freshman test scores as matric scores. So in America, they would write SATs, but here, before we go into university, we write matric. So now suppose you have this data. There are a number of different universities plotted here, and for each university they plotted let's say our matric scores and then the graduation rate as a percentage. So what percentage of students graduate? Now this is a confidence interval that you get, so go through the working and just see that you agree with it. It is just direct substitution into the formula, and what this tells us is for a 1 point increase in matric score or rather SAT score, then you can expect that the graduation percentage will go up by between 0.063 and 0.114%. Remember, graduation rate is given as a percentage. So that's what the slope tells you. So instead of giving a point estimate, now you know you have a range of possible values that are associated with a 1 point increase in your X value. We're done with the confidence interval, so now let's have a look at the hypothesis test. This is a typical hypothesis test that is exactly the same as the previous ones you've done before. So you can expect that your null will look exactly like this. So we're going to test that beta 1 is equal to some value. So this beta 1, 0 is your null value, and it could be any value, positive or negative. And then the alternatives are these typical options. So it'll be any one of these depending on the question. And in order to make a decision, you need your test statistic and a rejection region. So this is your test statistic here. So you just need to calculate this value. Remember, we said it has a t-distribution with n minus 2 degrees of freedom. So you'll get your rejection region from your t-tables. In order to find a p-value, then you're going to do it the exact same way as you would do as in chapters 9 and 10. So for example, in this first case, it's a one-sided test. If you wanted the p-value, you would take the test statistic value and find the probability to the right of that value. In this case, if you wanted to find the p-value, you take your test statistic and find how much probability is to the left of that value. And then for the two-sided one, you take your test statistic, find how much probability is, let's say if you have a negative test statistic, then how much probability is on to the left of that test statistic, and then you double it. If you get a positive t-value, then you find how much probability is to the right of that test statistic value, and then you double it. So you will be expected to be able to do that. You'll also be expected to be able to make a conclusion using your confidence interval. So you do it the exact same way as before. Remember, if your null value is in the confidence interval, then you will not reject. And if it's outside, then you will reject. I just want us now to focus on this little point at the bottom. This point is highlighting just a special version of this hypothesis test. If you take your beta 1, 0 to be the value of 0, so in other words, there's no slope versus there is a slope. That's exactly what you're testing here. You're not testing whether it's a positive slope or negative slope, just does it exist or not. This special hypothesis is very commonly used, so it is given a special name. It is called the model utility test. So just bear that in mind. Everything else obviously remains the same, just your null value is just 0 everywhere. I'm going to look at it a little bit closer so you can just see what it means. But here, just remember, you can look at example 12.3 as an example to see how this hypothesis test is performed. So remember, if beta hat 1 is not equal to 0, that means there is a relationship between x and y, and it's given by a straight line. There actually is a slope. So if I tell you something about x, you can tell me something about y. But in this case, if I tell you something about x, that tells you nothing about y. So another way of interpreting this null hypothesis is that there is no linear relationship. So you see in this case, you can see that there is a straight line that's sloping up and down. So in other words, there is a linear relationship. In this case, there is no linear relationship. So you can look at H0 and H1 and interpret it in this way. So you could be asked to do this hypothesis test, but instead of stating, test whether beta 1 is equal to 0, I could say test whether there is a linear relationship between x and y, and it's just another way of asking for this hypothesis test. Now, there are two ways of performing the model utility test. So in other words, if you want to test this hypothesis, you can either use the t-test as discussed in the previous slide, which have the summary from page 648, or you can use an f-test. So you can actually construct an Anova table. that will give you the same results. So I want to show you how you do that for regression. So this is your Anova table for a simple linear regression model. So it looks exactly the same. You have a column for your source of variation, your degrees of freedom, your sum squares, and then your mean squares, and then your test statistic. So from your computational formulas, you should be able to calculate SSE and SST. Okay. So now to populate the rest of the table, let's find the regression sum of squares. So remember, the regression sum of squares is SST minus SSE. So you can calculate that one just from SSE and SST. Now, the next thing you need to know is your degrees of freedom. This is the degrees of freedom. You need to memorize them. And just remember that your degrees of freedom for regression and the error, if you sum them, they should give you your total degrees of freedom. So just make sure you don't make a mistake by just verifying that this holds. Now remember, in order to get a mean square, you take the sum of square and divide it by its degrees of freedom. So in this case, obviously SSR divided by 1 just gives you SSR. And if you take SSE and divide it by n minus 2, it'll give you MSE. But remember, MSE is this estimator for your variance. So in other words, it's S squared. And in order to find your test statistic, you take this mean square and you divide it by this mean square, and you end up with this value. So now you have an F test. Your rejection region, which you need to memorize, looks like this. So for an alpha level test, it is always going to be a one-sided test. Okay, so even though it's a two-sided test here, your rejection region is only one-sided. So you just need to memorize this. So all of your alpha goes there. You don't split it. You only test for large values of F. And your numerator degrees of freedom is 1, and the denominator degrees of freedom is n minus 2. So if you get a test statistic value that's greater than this value, then you're going to reject. So you should be able to construct a table like this. If you go to page 649 in your textbook, they discuss this further in a small paragraph. So let's just compare the two, your t-test and your f-test. There is a relationship, a very clear one, between the two. So regardless of which way you do this test, you should get the same conclusion for this hypothesis. So let's start off by comparing test statistics, and then we'll look at the rejection region. So remember, our test statistic value, if you're doing the t-test, is going to be this value, and if you're doing the f, it's going to be this value here. And these two values have a special relationship. F is equal to t squared. So whatever you get here, the square root of this thing will give you t, and if you get this thing, if you square it, it'll give you the f, test statistic value. So just remember that. Sometimes we do ask that. And then if you look at your rejection regions, so if you focus on this value, it's exactly the same as this value, but this one is negative. So this value, if you square it, so similar to that result there, then you actually end up with the f value over here. So you can actually get your rejection region as well if you know this value here. So these are just two relationships that are very interesting, and you should know them, and you can just keep them at the back of your mind because they do come up in test and exam questions.